moves it that way, that moves it that way. Cool. Right, we're going to start now. It's 10 past. Let's roll. Okay, cool. Hey to everyone. What we're doing today is doing hypothesis testing with a normal distribution, and it's the very, very last topic of the entire course. So as of today, we are done. Okay, well, if you understand this, we are done. I mean, I've asked everyone to email me or get in contact with me one way or the other, just to see what people would like for their revision classes, what subjects. And thanks to those people who've done it, I know Evie's done it. I know a few others have done it. If those guys, if you haven't got in touch with me about that, let me know, or just drop me an email or whatever, or use Microsoft Teams, whatever you feel comfortable using. And I will catch up. It's good to see you, my dude. But who the hell is Stitch 'em Up? Names are helpful, right? Because Stitch 'em Up doesn't tell me anything. I mean, it gives me an idea, but I'm not going to guess who it is. Right, okay, cool. Let's start. So first of all, what is hypothesis testing? It's the same thing that you know from binomial distribution. I hope that's relatively fresh in your mind, where we've got to create a null hypothesis, an alternate hypothesis, H0, H1, and we test to see whether it's whether we've kind of breached the null hypothesis or the alternate. Yeah. Now, what else do we need to do? We have the same sort of percentages that we're used to. So 1-tailed and 2-tailed and 5% and 1%. So all that stuff from binomial distribution that you know still exists. That's still in the game. So all that information is like sunk information, right? So you can rely on that. Now, what is the first thing you need to know? Well, the idea of first thing you need to know is that the normal distribution, let's say for a population which has got mean of mu and variance of sigma squared, can be approximated for a sample with x bar. So your sample mean, so your sample distribution would be normal distribution with mu the same, but your variance would be sigma squared over n. So if you've got a population and you want to do something about sample, you need to change your variance from just being sigma squared to sigma squared over n. And that means that the standard deviation would be the square root of sigma over n. So it's the biggest common mistake to make when you're doing hypothesis testing, when you've got a sample, is to keep the sigma squared the same. It's not the same thing. It is now sigma squared over n for the variance, so therefore sigma square root sigma over n. What's the variance? It's a number that they give you. It's basically just the standard deviation squared. Yeah. So the variance is just the standard deviation squared. All right. Is that enough to clarify? Do I need to define what standard deviation actually is in terms of what it does in mathematics? So I can do that if you want. N, what's n? N is your number of things in your sample, and that's always the same for n's. You know, so when we did binomial, it was like you had a sample of 20, n would be 20. Yeah. Anything else anyone's unhappy with, just kicking off. So if you had a population, remember population's everything, and then you took a sample for it. If the population is normally distributed, the sample will also be normally distributed with the same mean, but instead of having sigma squared, you'd have sigma squared over n. Is the n in the square root? No, sir. Who the hell is Clorox bleach? Names. It helps. I'm not going to remember all of these. I can't remember what the other guy was. Anyways, who's confused? If you're confused, you need to say so, and you need to say what you're confused about. I don't even have your faces to guide me on this. All I've got is what you write in a textbook. Okay? So there's clearly a couple of people that's confused here, but if you just leave it at there's not a lot I can do to help you, right? So talk to me. I'll give it a few more seconds, and then I'm literally just going to carry on, right? So make sure if you're struggling with the idea, sigma squared over n, what the hell does that even mean? Right, in English, right? If you have a population of data that is normally distributed, right? And then you take a sample of it, yeah? You wait a minute, Saul. So let's start. So as Louise said, X was a population, and that population is normally distributed with your mean as sigma and your standard deviation, so your variance as sigma squared. And then you took a sample out of it. You could do calculations and assume that sample is also normally distributed, yeah? So the sample you took out of the population that was normally distributed is itself normally distributed. It would have the same mean, but its variance would be sigma squared over n, yeah? Now, why is SD that? What do you mean, though? What does that actually mean? Remember, as I said, all I've got is your 4 words there. Why is SD that? Why does it change? Due to the fact it's a sample. Yeah, so the sample obviously doesn't have the same size as the population, so you're going to have to trim down the variance by some extent. In fact, that's actually called the standard error, if I remember correctly. You don't need to stress too much about that. Just bear in mind that that is the change. You won't be asked to prove it. Yeah. So if you've got a sample size n for a population, your mean would be the same, and your standard deviation would, so variance would be sigma squared over n. All right. Anyone got any further questions on this before I move on? I'm going to give you 30 seconds just to type them in. Yeah. While you're taking that time, I'm going to restate the main idea that we've got so far, which is if X is normally distributed as a population with mu and sigma squared, if you take a sample out of that population, call it X bar, then that too will be normally distributed with mu as mean and sigma squared over n being the variance this time. And if sigma squared over n is the variance, then we can say that the standard deviation is sigma, and so root sigma over n. All right. So what I'm going to do is take you through two examples. I'm going to take the ones in the textbook because that means you can read along. So if you've got your pack with you, I'll give you a few seconds to find it if you haven't. Page 56 is the one. All right. So page 56 is the one. I'm going to try and hold this up so the camera shows it at its best light. I'm not sure how well that'll work. If it doesn't, I might just, I'll hold it so I can read it and then assume that everyone's got the pack. So take about 30 seconds, grab the pack if you haven't got the pack with you. And it's example 14 on page 56. I'm going to read it together. All right. All right. So I'm assuming that you can all see example 14. You probably can't see it very well on the screen from what I can see. Maybe you can, I'm not sure. I'm going to read it to you in any case. So it says a certain company sells fruit juice in cartons. The amount of juice in a carton has a normal distribution with a standard deviation of 3. The company claims that the mean amount of juice per carton, mu, is 60. A trading inspector has received complaints that a company is overstating the mean amount of juice per carton, and he wishes to investigate the complaint. He takes a random sample of 16 cartons, and he finds the mean amount of juice is 59.1. So this is your standards kind of question where you've been asked to test a null hypothesis. What is a null hypothesis here? It is that the amount of juice per carton is 60 milliliters. So H0 is mu equals 60, right? And your alternate hypothesis, this here will be a one-tail test, because you want to know whether it's understating the amount of juice that should be in there. So we're assuming in this case that what is the probability of being less than that mu is actually less than 60 milliliters. The question asks us to use a 5% level of significance, and we need to state our hypotheses clearly, test whether or not there is evidence to uphold the complaint. So let's think about the first 2 marks you can get straight away. You should be able to state that H0 is 60 and H1 is less than 60 to get 1 mark. You must further be able to say that we're doing it as a one-tail test. Okay. Now, if the normal distribution for the population is as the null hypothesis would say, then X would be approximated by the normal distribution with a mean of 60, mu 60, and standard deviation of 3. So you'd write variance 3 squared. Yeah. That's the population. That's why I'm not dividing by n here. But for the sample, I would divide by n. So reading the question again, it says the trading inspector takes a random sample of 16 cartons and finds a mean amount of juice. So 16 is n. So for our sample, and the sample is always given by using the same letter as the population, but with a line on top. So X bar this time, X bar tilde n, mean will be 60, and variance will be 3 squared over 16. Now I realize me reading this isn't the ideal way of doing it. So what I'm going to do is I'm going to read them all out, and this time I'm going to write them on the whiteboard. All right, so that will give you a chance, if you haven't got the pack, to understand what the hell's going on. So the question tells us our null hypothesis is that mu is it 60, isn't it? Yeah. And our alternate hypothesis is that we don't believe that. We believe that they're overclaiming. There's not enough juice that they're saying it's going to be. All right, so that's really clumsy English. I apologize for that. So they've called the variable X is no, and this is the population. Be clear on that, yeah. 60, and in the question it says it's 3 milliliters for the for the standard deviation, so 3 squared. So this will be your population. You vary that in only one criterion for the variance. I mean, for the sample, you only vary that for one little thing for the sample, and that is to say, well, X bar, which is the sample distribution, would have the same mean, but this time you're going to be dividing by 16 for the variance, right? So I hope that makes sense so that you see that quite clearly. There we go. All right, a little bit better. Okay, right. Are we happy? Yeah, I mean, the tilde's not the problem. Do you understand the rest? I mean, can I just get a little bit of confirmation on that from you guys? Like, so what I've said to you is we're looking for example 14, and we get to here, we get to the null and alternate hypothesis relatively easily, and we use the idea that I've just taught you to work out. Fair enough. Right, I can only hear from source. So can some other people pop up and say whether they understand or not? All right, because that's kind of fundamental to the next bit. Brilliant, Louis. Why is it? Wasn't it square rooted in the first example? Now let's be absolutely clear on this. When we do it inside the brackets, we're working out the variance. When I do the standard deviation, I'll square root, because the standard deviation is the square root of the variance. So yeah, you will end up with 3/4. Okay, is that making sense? Yes, please. So let's get it bouncing in here. Quite right. Yeah, we're all happy with that so far. Brilliant. Okay, cool. So now we're actually going to do the hypothesis test. So I hope everyone's comfortable with that. So let's take a look at, hopefully you've got the pack with you. Ooh, where's my arm? If you've got the pack with you, you'll be able to read the box. So what I'm going to do is I'm going to read it out, then I'm going to go through it on the whiteboard with you. All right. So what does it say here? We work out the probability of being 59.1 or less, and that's 0.1151. So the question you would have done there, just to write on the whiteboard for you, is that we're going to use x bar is 63 squared over 16 to test the probability of being what was it, 59.1 is what it turns out to be. And if you do that, the chance of that happening is 0.1151. Now that's bigger than 5%. So we're not going to reject the null hypothesis. That's relatively simple, isn't it, as a concept? I hope that makes sense to you. Yeah? Okay, Eve wants me to go over it again. Why is it 59.1? Because that's what it is in the question. If you look at I'll read it out to you. The trading inspector takes a random sample of 16 cartons and finds that the mean amount of juice per carton is 59.1. Okay, so that's why it's 59.1. Okay, now I'm going to deal with Eve's question. So can you go over that again? What in particular? Is it the whole thing? If it is just, okay, you're happy. Eva, can you just tell me exactly what you want me to cover? I'm just waiting on Eve to let us know what you want. Okay. I mean, if I knew who you were, I'd advise you to drink it, my dude. The standard deviation bit. Can I get fired for telling a student to drink bleach? I don't know. I mean, it depends what it is, really. Yeah, fine. Okay, you know, for the normal distribution, it goes x sigma n kill yourself, mu, okay, suicide threat as well, mu and sigma. Yeah, does that make sense? Squared. And that's the issue, because that's the variance, right? So the variance goes, so in this case, the variance would be 3 squared, yeah, over 16 for the adapted data, yeah? So this is your population, right? Let's keep it simple, yeah? If you want to work out your variance for your sample, it's n squared, sigma squared of n over, sorry, yeah, forget the words I'm saying, look at what I'm writing. So this is population, this is sample, right? And obviously, if this is the variance is the SD squared. All right. So if I want the standard deviation, I've got to square root whatever the variance is. That's where you get things like, for example, this guy, sigma over root n. Yeah, I'm sorry if you can't see that last little bit. I'll write that out a bit bigger. So if you realize, because the variance is the standard deviation squared, if I need to do a calculation with the standard deviation, I need to go to my variance and square root it. The square root of sigma squared is just sigma. Well, that's fine. But the square root of n is root n. And that's why there's a square root there. Is that making sense? Let me know if that hasn't. So all I'm saying to you, we'll just repeat it one more time, is that the second thing in the column, in the bracket, is variance. But I do calculations with a standard deviation when I'm doing normal distribution. Can you see it now? Yeah. Sorry about that. I am wearing the camera, and that's why it gets a bit weird sometimes. Can you see it now? So all that missing line was that variance is standard deviation squared. All right. So all I'm doing here is square rooting this guy. Okay, are you happy with that now? Yeah. Were you okay with all the rest that followed after that? Just doing the normal calculation, seeing that it was 11%. 11% is too big to reject null. Or do you want me to repeat that as well? I mean, I don't mind. I'm not getting paid for this, but who cares? So it's, yeah, it'll be sigma over root n for the standard deviation of the sample data. And you can remember that. It just is that. Might be worth writing that down. So for the sample data, I do want to write it down just without context, but that's the sample SD, which I think is called the standard error, but I don't think they use those words anywhere. So I'm not going to myself. Yeah. Hopefully that makes sense to you. Tell me if you're ready to move on, everyone. All right. Oh, I got a random Sky News update. That could have been more interesting, to be fair. We good? Just drop a message in the comments if you're ready to move on. Or the live chat, not comments. Can't read comments midway through the live stream. Let me know if you're ready to move on. Right, go over the rest of the example again. Okay, cool. So we now know that for our question, mu is going to be, what was it? Still 60.1. It's just 60, isn't it? And our standard deviation is root n. Well, the next one, yeah, it doesn't need a Spidey sense. If you look at example 15, all hell is about to break loose. And that just becomes 3 over 4. Yeah? How comes root 9 is 3, root 16 is 4? All you now need to do is go and just remember what you know from before. You know how to do this already. What is the odds of, what is the probability of 59.1? And if you do that, just use simple normal distribution using these parameters, you'll get that that works out to being 0.1151. However, you know from the past that to defeat a null hypothesis, your probability has to be less likely than 5%, in this case, because it's a 5% test. This is not ideal. That may be better. Yeah, that's better. Okay. Really got to sort something out with this camera business. So we're not going to reject null because that percentage is just too high. It happens 11% of the time. That's not insane enough to reject the null hypothesis. We want to be rejecting the null hypothesis at about less than 5% because there's a 5% test in the question in the pack. The pack tells us the question is run a 5% test. So we can't reject the null hypothesis here because 11.21% of the time this would happen just by luck. All right. Is that now satisfactory? So if you just do the standard normal thing that you learned, literally in the first lesson of normal distribution, working out the probability is less than or more than or whatever, and you find out that that is 11.51, you can reject the null. Yes, I've gone. So what's wrong with the test, my dude? Do you use them? Yes, because it's the sample that you're analyzing. Yeah, absolutely. Be clear on that. Yeah, but the mean is going to stay the same. There's not even a case of the old mean. There is one mean throughout. Yeah. Is that now okay? Okay, brilliant. Okay, the second one is considerably worse. You hope it's a representative sample, but yeah, it is. I mean, they don't make that kind of explicit, really. There's something called a central limit theorem that says it should be 30 or more, but you know, we're not going to get into that. You only need to worry about that if you're going to do a degree. Okay, cool. Let's move on. Example 15. So here, again, I'm going to read it out to you. I'm going to try and put it up on so you can see it. So example 15 is found on page 57, and this one is considerably worse, all right? And if you look at the example, it's one of those ones that doesn't sort of follow straight away. So we need to kind of go through ourselves. All right, cool. Let's try and get this as, I don't know if you can see any of that. I don't think you can, but you know, I can read it, and that's a good place to start. Right, so we've got a machine that produces bolts of diameter d, where d is a normal distribution with mean 0.580 and standard deviation 0.015. So let's create that. So we've got d is normally distributed 0.580, 0.015 squared. Yeah. Okay, so I can now see Husner's on. The thing about using Microsoft Teams Husner is there's no way I can read it, okay? Because like I'm struggling with the technology of a whiteboard. To read two separate group chats is a bit of a push, but thank you for letting me know you're there. So what you can do, if you can't get on YouTube, do one message like that, and then I'm just gonna have to ignore you, I'm afraid. Okay? But thank you for doing that. I really appreciate it. Okay, cool. So that's what we've got from the question so far. Let's read the rest of it. It says the machine is serviced, and after a random sample of 50 bolts, the mean. So they want to see if the mean diameter has changed. Yeah. And the distribution of diameter of the bolts after service is still normal with distribution of 0.05. Yeah. So they haven't told us how it's changed because they're asking us to do something different. They're asking us to work a critical region, and this is a little bit harder. So I need you to walk with me step by step. It's super, super important if you've got the pack with you. All right. So like if you haven't got the pack with you, I mean, you're gonna have to go with me as best as you can. But it just take the lesson of it. We should have textbooks really, but the pack is the next best thing. Okay, cool. Find at the 1% level. So the question says, has it changed? So that's a two-tailed test. All right. Straight away we know that's a two-tailed test. We want to find the critical region. Remember, the critical region means the region that you have to land in order to reject the null hypothesis. So it's not like the other example where we just, worked out the probability, we flat out said it was less than 5%, or so more than 5% rather, so we don't need to reject null. Now we're finding out where things are, all right? And if you're following the pack, the first thing that they do is work out what D bar is. So I'm going to do that with you right now. The sample size is, how many, 50? So we can go straight away to go to D bar is n 0.580, 0.015 squared over 50. And of course, if I wanted to work out the standard deviation, which I will eventually need to do, I would have to do the square root of that. So I hope that's making sense to people. All right. So that's what you've got here. So far, so good. Next thing. The next thing to do is standardize. All right. The reason why we're going to standardize is it's a 1% test as it stands. So we're going to need 0.005 as our standard, as like half and half each way, right? Because 1% will split to make that. But that's one of the things that's a standard information that they give you in a table. So you don't even need to mess around with a calculator. So the table, however, only works for the standard normal. So what we need to do is standard normal it. And you remember the formula for this is Z equals, well, in this case, it'll be D bar minus mean over sigma. And just to make sure everyone's absolutely clear, it's the new sigma. So it'll be 0. I'm going to try and put that back into shot. 0.15 over root 50 is your sigma. It is not your population sigma. It is definitely your sample sigma. All right. So once you standardize this, and I want you to do this for me, you should get that Z equals minus 2.5758. So I hope that's making sense to you. All right. So can you do that for me? Can you prove to yourself that you would get the same thing I would here, or the textbook would, and got the Z equals minus 2.5758 rather. All right. I'm going to just hold on for it. So run it back. Standardize again, please. Okay, cool. The standardization formula is this guy. Yeah. Whatever you've got minus your mean over sigma, right? So here we're going to get that we have got D bar here, which is our distribution here. All right. We want to find out for 0.05. Yeah. And what is 0.05? 0.005 from the table. Does anyone know what that is? Okay, no worries. No worries. I think I've gone a bit too fast with that, so I better do some explaining. So 0.005, yeah, on the standard normal table. And if have you got your formula booklets with you? Otherwise, I'll just tell you what this is. Okay, I think I'm gonna have to tell you what it is. Would give you a Z bar value of 2 minus 2. So it's just a z value of it, sorry, minus 2.5758. Yeah. And what does that mean? It means that for the standard normal, the value at which only 5 in 1,000 or 0.5% is below that is minus 2.5758. Yeah. If you're struggling with this, we almost have to go back to standard normal and what it does. Remember, standard normal is the one where mu equals 0 and sigma equals 1. Yeah. And we use it because it's comfortable to have one that we can all base everything else on. So for a 1% two-tailed test, we break it down and get 0.5% each way. 0.5% on the standard normal table is minus 2.5758. I hope that makes sense to you. Yeah, is that making sense? Let me know. And then I'll show you how to do the calculation. But I don't want to do the calculation until I'm sure you understand this bit. There's a table in the formula booklet that just hands it to you. Yes. I mean, you can do it on the calculator if you want. I'm quite happy for you to wait and prove I'm right by doing it on the calculator. How would you do it on the calculator? Again, it's area, isn't it? Well, actually, no, hold a minute. Yeah, you already know the area, so it'd be inverse normal, wouldn't it? So 0.005, mu equals sigma, mu equals 0, sigma equals 1. Feel free to do it on a calculator, yeah? Because the calculator is no slower, especially if you haven't got the formula booklet with you. I sort of assume that you have everything you need, and if you don't, if you have your white calculator, that's all you're going to need. So just do inverse normal with mu equals 0, sigma 1, and area 0.005, and you should get minus 2.5758. Tell me if I'm wrong. So if I'm wrong, I kind of need to know. So can you guys either check your table, prove that I am right? Good, Alex. I'm glad to know I'm not wrong. But to be fair, if you want to use your calculator, do that as well. Yeah. So I want you to have a method that you are comfortable with. End of the day, right? Okay, cool. Now what we're going to do with that? Here's how we do it. We now know what the z value is. So we're in the unique position of actually knowing what our answer is. And all we need to do is figure out what we're after. So x bar, which is the thing we were using before, minus mu. Let me just remind myself of what mu was. Mu was 0.0580. So I should really have written those down somewhere. And you've got 0.015 over root 50. And you just solve and find out what x bar is. Now, where did those numbers come from? This is the thing we're looking for, the critical region number. This is the mean, and this is the standard deviation. And where did this formula come from? It's your old beloved standardization formula. Whatever it is, minus mu over sigma. All right? So that's where those numbers come from. So if you're confused, where the hell did all this come from? It came from, well, if I want to standardize a variable, in this case x bar, I subtract the mean and I divide by the standard deviation. Just to make it once more explicitly clear, it's not the population, it is the sample standard deviation. So that's where the calculation I'm getting for. Now the textbook informs me that this number is 0.5745 is your final answer. Would you care to confirm that for me? So 0.5745 is your final answer. Please let me know if you've got that. So all you need to do is find what x bar is. Brilliant, brilliant. So what you've done there with that 0.5745, do you mind if I just wipe this? I mean, remember, you can always go and watch this again, is you found the lower bound of your critical region. So your mean is at 0.5, I need to remember the bloody thing, 0.580. So that's your mean there, right? At 0.5745, you've got your lower 0.5%. Okay, now by symmetry, it should be obvious what we're going to do next. We're going to do exactly the same thing, but this time with positive 2.5758, because that will give us the top half, literally the last 0.5% here. So again, I mean, you could probably just do it by symmetry and work out what that number is by sums, but like, I'm just going to show you the formula one more time. 2.5758 equals, what have we got there? We've got x bar, which we don't know. We've got the mu equals 0.580. Let's check that is 0.580. Yeah, it is. Over whatever the new standard deviation, which I think was 0.015 over root 50. And that's how you get the other bit. All right, and those two numbers, the 0.5748. Why can't I say numbers? Yeah, 745. Sorry, 0.5745 rather. Let me write that down so I don't forget it. That's the lower bound for your critical region. So anything below that, you're rejecting null. And then here you can work out exactly the same calculation, this time with a positive version, because you want the top 0.005. Do exactly the same calculation and work out what this number is. I'm just going to go and check it because my calculator will take effort. And this time it was 0.5854 at the top end. So your test now is, can you get the same number? And do you understand? Yeah. So the answer is 0.5745 for the lower bound of your lower critical region. So anything below that would reject null. And your upper bound will be 0.5854 for the upper bound. All right. So can you check by doing the second calculation that you get that? Because if you do, that's great, and I can shut up almost. There's only one tiny thing beyond that to show you exactly how to finish it. If you're struggling, say so, because this is the harder one. Why are we adding the mean? Why are you adding the mean? That's a very good question. I don't know why you're adding the mean. I mean, all I've done is reversed the question around and said, well, look, if it's the top half, well, there's one very, very simple way. You could just done it straight by symmetry. Oh, well, what have you got there? I'm slightly baffled by this. All I've done is invert. All I've done is I already know what the normal distribution of this is, right? 0.574. Let me just quickly check what they've done. All they've done is undo the normal distribution. Is what I told you to do. I'm saying not undo the normal distribution, undo the standard normal. So we've got the value as a standard normal from the table, right? Yeah, I know, I hear that. Yeah. And what they're doing is they're saying, basically, I've got the standard normal answer for this, but to go back to my actual question, I have to undo the standard normal. So all they do is put the standard normal formula that you'd normally have to do to the answer and basically invert it. Literally what Louis is saying. Yeah. You need to put the mean in. Yeah. Louis has absolutely just got it in much, much elegant way that I said it. You're rearranging the Z formula to get whatever you want. I don't even have a heart, let alone little. Right. We're nearly there. We're nearly there. We just got one last step and I'm going to shut up. Okay, cool. Are you now happy that you get the mean, that you'd have to do the mean? You're just undoing the formula. Yeah? Anyone else got any problems before I just bring this to a close here? Once I put an edit, you might want to kind of come back to this for an edited version. It's like the first 5 minutes from you waffling about coronavirus. Basically, don't worry about coronavirus for today. Tomorrow, it looks like we're in. It wasn't a systematic error, it was just a maths error. Fine. I mean, who am I to judge on that, eh? Okay, comment on this observation in the light of the data. So again, you just look at so part B says, it actually, when it turns out to be 0.587. 0.587, if you look at your data, falls inside the critical region, so you reject the null hypothesis. So once you've got your critical region, they give you an actual answer, say, well, look, this is what actually happened. Then you have to apply it. One of the things they say in the textbook is, don't just refer to the context. So remember to refer to the context question. Don't just say we're rejecting null. To get full credit in this, you need to say we're rejecting null, therefore, and then you start talking about bolts or whatever the hell question. What is this question about? Yeah, bolts. So like say the machine for bolts has changed. All right. So I hope that makes sense to everyone. This video is going to take a tiny bit of editing thanks to me like struggling with the camera. If anyone's got any questions, I'm going to keep the live chat on for a minute or two. So you can chat, and it's like questions about anything, college in terms of like coronavirus or the mathematics itself. I recommend got at least question 1 in 3G just to see if you've got this down, and then drop me an email or use the Microsoft Teams, which a few of you are starting to use now. And that's excellent. All right. And if you have sent me a message on Microsoft Teams, I'll chase that up about 6, 7. Because it will take me a little while to edit this video. So I'm going to leave live stream on just for a second. I'm just going to waffle for a bit. If you want to go now, you are free to go, because like I've covered all the content I need to. So like, don't feel free to be constrained to be here. The only reason you need to hang around here is, excuse me, if you're concerned about anything. And I'll shut this off at 45 minutes exactly. What class of integration? Yeah, let me hear your views on this just quickly. What I've done is I've created some of the nastiest single integrations that are in the textbook, not the gold, silver, bronzes. I left those for you. And what I was going to do is I was going to split the class in half, right? The ones who feel like they're good at integration, I was going to give you like full-on integration, exam level integrations. And the ones who are quite weak at integration, I was going to kind of basically personally tutor them, if that makes sense, so like get them in a school group and support. I don't know what you think about that. I'd love to hear it. So drop me a message, whatever you think. The other thing I'm going to say is that if you want integration, extra help on integration, and you're free from 10:45 onwards, come down to L33, and I'm teaching integration to my further maths class. And quite frankly, it will do them good for you to give them a good kicking. I mean, I probably have to delete that from the video as well, but you know. So yeah, if you want extra help with integration, there'll be some available at 10:45. At 1:15, there's going to be a full-on revision session for integration. And there's some real nasties in there. I mean, I did the work solutions, and I mean, Jesus God, there was one of them that's a real special. I mean, it was great fun though. It's about what? Integration. You were trained by me. You have nothing to fear, my dude. I mean, like, what is second deval? Okay, 05854. Let's have a quick look. Because what you're doing is just doing, instead of doing the minus 2.57, you're doing a plus. So you're going to do the formula you're doing is 2.5758 equals d bar minus 0.580, which is the mean over the standard deviation. Okay, that just might be that they've made a mistake. The mathematics is not incorrect, because if you look at what the mathematics they're asking you to do in the textbook, it's identical to what we're doing. I'd worry if they were doing some other thing. I'll say, yeah, this thing is equivalent, but it's not. Is there anything else that people are worried about? I mean, I'm more than happy to kind of like pop up a work solution for that. Yeah, I mean, I always try to bring down the establishment personally. All right, so as I said, I am done here. Any other questions? I'll hang around for about another minute. Look after yourself, my dudes. Well, that goes for all of you, right? Look after yourselves out there. There's a bit, I don't, from what I said from meeting that the A&A doctor, they're not panicking, but I think like the media is making people panic out there. So you just look after yourselves. Take care, yeah? All right. I'll hang around for about another 30 seconds in case anyone says anything. And then I'm done. Hey, here's my hand. Okay, that'll be a lot. Take care. Yep, definitely want to do that.